Yes, anyway, the work I'm going to present was done together with Johannes Jensen here at NTNU. It's in the area of material computation. We are trying to exploit emergence and self-organization in nanosystems. And we try to find novel computational system, new kind of computers. The systems we are interested in are complex dynamical systems with large amount of simple units. So we want them to display emergence and at a global observable level. To be able to measure computation, we need some way of quantifying it. And the system we use is the reservoir computing framework. What we do is we investigate tunability and scalability in a nanosystem. And the system we are interested in is artificial spin ice. Artificial spin ice are very promising as the computational substrate. They have been used a lot in experimental physics, but now we are trying to make them compute. Artificial spin ice is a regular grid with nanomagnets, as shown here, and they are organized in some pattern or geometry. And that kind of makes a system with magnets, nanomagnets. Here they are rectangular or stadium shaped, and they interact on based on local magnetic fields only in the nearest neighborhood. The magnet's length and thickness can be set so they act as dipole, or we call it spins. That is, they can toggle between two directions. That is a property that kind of we exploit to see the magnets as binary toggling units. One of the cool things with artificial spin ice is they can be produced as the thing we are seeing here, and they can also be observed in as physical system. As we see here is a kind of an image of magnet forced microscopy. So we can observe the magnetic state on the magnets. We can also simulate them. Sorry. We can simulate these systems at a very low level, a few atoms, but that kind of requires an extreme amount of computational power. So we can only look at systems of the size of 100 magnets maximum. Another thing we can do, we can take a higher abstraction level on the simulations and look at the magnets only as dipoles, 0 or 1. And then we are able to simulate magnet arrays of millions of magnets. That's the approach we have taken here in our paper. So this is all about computation. And to do computation, we need some way of having inputs and outputs. For these spin ice systems, we can have the input as a magnetic field. We can use some kind of amplitude modulation to put in zeros and ones, as shown here in the middle. Or we can kind of change the angle of the magnetic fields to code for ones and 0 as input bit strings. The behavior in this system is kind of what makes them interesting. Here is an example of two kind of similar but different systems. On the left, we have a kind of square system, a square spin ice. In these systems, we can kind of make the system behave like waves, so they are moving waves as the emergent property. Or at the right, we have kind of twisted the magnets 45 degrees, and we have a spin ice like structure. And then we get these kind of large spatial patterns as the emergent phenomena we are looking at. Further, we can tune these systems with changing the shape of the magnets and the distance between them. So what we are doing for computation, we use the reservoir computation framework. Our spin ice is a dynamical system, So it has a high dimensional output out of a low dimensional input, and we can use that to measure quantitative parameters like kernel quality and generalization. Kernels is kind of how good is the system to separate input signals, and generalization is how good is it to generalize or see similarity in these patterns. We need both for computation. So we are also computing the computing capacity Q. That's only a kind of calculated measurement out of the kernel quality and the generalization capability. In our experiments in this paper, we have used the pinwheel geometry of the spinel. So we have these large spatial patterns that we kind of use as the kind of behavior of the system. The number of magnets in our system and experiments are 220, and that's kind of fixed for all our experiments. And we also use a fixed field of the external magnetic field for each experiment, so we don't change it within an experiment. And we also use an angle as the kind of coding of zeros and ones for the inputs to the system. The two kind of measurements we do is kernel quality and generalization, and then we kind of calculate the computational capacity. In our experiments, we use a bit string of 100 bits, and we use 220 random bit strings that we generate to test the kernel quality. And for generalization, we also use 100 bit, but the first 40 bits are random and the last 60 are equal, to see how good it generalizes the last part of the input. The details for the artificial spinels is also given here. This is one thing that I would like to point out, is that we generate 30 spinels, slightly different, to kind of simulate production disorder. So all of the experiments are done for 30 slightly different spinels setups. We just change it a little bit to kind of simulate these defects in a possible production of a real thing. Sorry. In our first set of experiments, we just want to sweep the parameters to see how good these systems actually are for computing. And that is, we sweep the external field strength, how big is the field that we use to code for zeros and ones. Remember that it's an angle that actually decides if it's a 0 or 1. And we also look at the alpha parameter, that is how close are the magnets. So what we have done, we have sweep these two parameters and made heat maps of kernel quality and generalization capacity, and also calculated the computational capacity. So the third heat map Q is actually calculated out of kernel and generalization. So what we can see is we get this ridge of performance in all of these. So there are areas where we can find good kernel qualities, and there are areas with good generalization, and also the kind of calculated computing capacity. So what we have done on the plot there is to take each of these ridge lines, and then we have plotted them as a function of the alpha value to see how the different parameters influence computation. So we can see we have this kind of bump for where we have both quite good kernel quality, and we also have good generalization. So by doing this, we have kind of shown that we can tune the magnetic fields and the alpha, the kind of closeness of the magnets, to make system that is actually quite good computers. So but the one thing that is kind of even more important, we'll show that we can compute, is can this scale. It's a kind of a fundamental thing if we want to look into building computers. So what we have done, we have kind of kept our system constant with 220 nanomagnets. And then we scale the number of magnets we kind of pretend are in a node in our network. As shown here on the left, from 1 magnet, or 1 spin, 4 magnets, and 12 magnets. So by doing that, we can kind of put a imaginary grid on top of our spin-ice system, like shown in the middle here, with a 7x7 grid. There is 4 magnets in each cells, and out of this we can calculate a vector with magnitude and direction. And then we have a kind of finer grid. We don't have the binary output anymore. We have a vector output with magnitude and angle. And that is what we use as a kind of parameter for scaling our system. We increase the number of magnets and resolutions within one node. And then the important thing is, since we keep our system constant, we will scale, we will also scale the number of nodes. So when the node have more magnets, we get fewer nodes in our system. Hope that was understandable. For one thing that is extremely important if we want to build physical computers is that we can scale the system without scaling the numbers of inputs and outputs at the same time. So if we want to do something more complicated or more complex computation, we don't want our system to have to scale up the number of inputs and outputs. There is not possible to build a system with millions of input-output lines. So by doing this, we also kind of can increase the computing capacity in a node, and at the same time keep the number of readout probes at a reasonable level. So then, how does this actually scale? What we have done now, we took a sweep first for to find the strength of the field and the alpha, the distance between the magnets, and we took a baseline of a grid by 5x5 RC grid, like the imaginary grid you saw on the previous slide. And we use that as a kind of baseline to set the coupling strength, the alpha, and also the strength of the external field. And then, does this actually scale? And it's kind of really nice that it does kind of scale. I would say that we are able to scale up the number of magnets in the node, at the same time scaling down the number of nodes without losing that much computation capacity and or kernel quality and generalization. I have to say that when we do this, when we scale the number of magnets or nodes, as seen in this plot here, from 2 to 220. 220 is full visibility. All magnets are used in the measurements. And at the bottom here, we have 2 kind of nodes, observable nodes. By doing this for kernel quality and generalization, we also kind of scale the number of nodes and also the number that we use as a benchmark. So all the numbers in these experiments are normalized between 0 and 1. So to conclude, I hope I haven't used too much time. Our artificial spin-ice is actually quite good computers. We have get very good results on established measurements for reservoir computation. We find evidence of fading memory, echo state property in these systems. And then the kind of really neat thing is the computational capacity is kind of obtained when we scale the number of nodes down and the number of magnets within a node up. We kind of see this as a kind of having a constant system with a kind of theoretical max computational capacity given by our 220 magnets, and then we scale up the number of magnets in the node and down the number of nodes. And we are actually able to obtain the computational capacity in the system with this scaling. Very promising, I would say. And especially that we find this echo state property in the system. I would also say that it's kind of another kind of artifacts of our way of setting up the experiments is that we see computation from the small scale dynamics when we have all the spins or magnets visible to when we use large scale spatial patterns as the kind of emergent property we use for our computational or our computational property in our system. And also just point you to flat spin. That's a large scale artificial spin eye simulator that we have made. It's available on GitHub, so I hope others are interested in looking into these systems. They are really fascinating and really cool. Thank you very much. Is there time for questions, or is that in chat?
Thank you. Yeah, if we can take one question if anybody has a question, but of course people are welcome to just put them in the chat, and then you can answer afterwards too.
Yeah.
So if anybody does have a question, just go ahead and raise your hand or unmute yourself. All right, cool. Well, if anybody, again, does have a follow-up question, feel